In this lesson, we're going to revisit the idea of separate and integrate. So this is the strategy we use to solve a differential equation when it is what we call separable. That means the variables can be separated from one side to the other. So that's what we're using, separate the variables and integrate each side. So this is when you have a product. Okay, this only works with products. It does not, or I guess with quotients, because quotients can be written as products when you multiply by the reciprocal. It cannot work on adding and subtracting. So I just want to lay that out there. Separate and integrate. You can't separate variables with addition and subtraction. It's only by multiplication or division. So we take all the dy terms and we separate them onto one side, and then we take the x terms and we separate those onto the other, and then we anti-differentiate each side with respect to its variable. All right, so all the y's will get a derivative, antiderivative on their side, and all of the x's will get an antiderivative on the other. So we'll just practice this as review. You've seen this before, but let's take a look. Sometimes things don't look like they are products or quotients. For example, this 2y minus x doesn't immediately strike us as a product or quotient, but it is, because you can write this as e to the 2y divided by e to the x. So this is a quotient, and it does mean that we can separate these two variables. So we'll end up with dy over e to the 2y, and then we'll end up with dx over e to the x. We'll want to rewrite each of those as well before we do our antiderivative. So we're going to rewrite this as e to the negative y, 2y dy. Just easier and a better form to have an antiderivative when the exponent is written with a negative power. On the other side, we'll have e to the negative x dx. And then we're going to integrate both sides. On the y side, the antiderivative of e to the negative 2y equals e to the negative y, natural log of e, and divided by the chain rule of negative 2. E to the negative x will have an antiderivative of e to the negative x, also divided by natural log of e, and the chain rule of negative 1. And then we have our ever-present constant of plus c. The last step, or steps, is to work towards getting y by itself. So we know that our natural logs both have a value of 1, so we can simplify those. And then we're going to want to multiply both sides by negative 2 to get rid of that. So we'll have e to the negative 2y. And when we multiply by negative 2, we're going to get positive 2 e to the negative x plus c. We're going to apply a natural log on both sides. And when you do a natural log, make sure it's around the quantity of 2e to the negative x plus c. So make sure that your plus c is in the quantity, not outside of it. So our answer, finally, with y by itself, would be y is negative 1/2 of the natural log of the quantity 2e to the negative x plus c. There are a couple different ways you could write that. You could write the natural log of 2e to the negative x plus c to the negative half power. That negative half power could also be expressed as a rad, I guess. So you could say it's the natural log of 1 over the square root of e to the negative 2e to the negative x plus c. I know there's a variety of ways you could put that answer. I feel like the first way is probably the cleanest, but who knows how they're going to want to express that. So be flexible when you're looking at the answers, the solutions to this one. Our next example involves a couple different strategies. we are going to want to start by separating. We should recognize that the quantity 1 plus y squared, we don't want to subtract y squared. That is not the right way to get y to the other side. We want to divide. So we're going to have 1 plus y squared will be our division. Okay, make sure that you're not thinking about subtracting. That would leave 2x and e to the x squared on the other side. After we've successfully separated, we will integrate. The left side, you might be thinking, oh, partial fractions, just because we just did partial fractions. But go back even farther. It's not partial fractions. This is inverse tangent. So this would be the inverse tangent of y is its antiderivative. On the right side, this product is something that's going to need a u substitution. And so x squared is what we assign as our u. We're picking that highest power. So 2x would be the du dx, which means that, oh, I realize I don't have a dx. There we go. Forgot that. Our dx by itself is going to be 2x du over 2x. So then we're ready to do a little substituting. So 2x is not impacted yet, but we'll have 2x e to the u. And then times dx, which is du over 2x. So this is going to be a nice, clean antiderivative of e to the u du. So our inverse tangent of y would then be e to the u plus c. So changing that back, that would be e to the x squared plus c. And then isolating y means we'll apply the tangent on both sides. And again, make sure that you are including parentheses so that the plus c is part of the quantity that you're taking the tangent of. Okay, our third example includes something that's going to enable us to go a little farther. We are given what's called an initial condition now. So we're given values for x and y that are going to help us find our plus c. So we'll go through the separate and integrate, and then we'll be able, after we've completed the separate and integrate, then we will solve, before we get y alone, we're going to solve for c. So let's take dy and divide it by y squared, which is going to give us x squared dx. I'd like to rewrite this as y to the negative 2. So let's write this as here y to the negative 2 times dy. Then we're going to integrate both sides. So this will be y to the negative 1 divided by negative 1 and x cubed over 3 and plus c. This is where I'd like you to find your plus c. Before you do any work of getting y alone, what we could do is we could rewrite this as negative 1 over y. That would be okay. But don't work towards getting y alone until after you get c. It's technically not wrong. It's just going to be easier and less messy if you get your plus c right now. So this is where we're going to plug in. And we're going to plug in x is 0 and y is 3. So that'll give me negative 1/3 equals 0 plus c. So c is going to be negative 1/3. So then I can go back to negative 1 over y equals x to the 1/3 over 3 minus 1 over 3, which would be better to write as a common denominator fraction So let's go ahead and put this as x cubed minus 1, both together over 3. Now, we want to get y alone. I always recommend cross multiplying just to make sure you don't, it's less likely to make a mistake. So that would be negative 3 equals x cubed minus 1 times y. So then y by itself would be negative 3 over minus 1. And so that's our solution for y being alone. I guess what I'm trying to help you avoid, let me back up a little bit here. Back when we were this way, I have seen students just simply try to flip every fraction upside down and think that they're going to get the right answer. So they flip this to negative y, they flip this to 3 over x cubed, and they flip that to 3 over 1. Those are not equal, those are not equivalent. You can't simply take the reciprocal of individual fractions. So that's why I usually recommend cross multiplying, because if you even thought about doing that, or if you thought that might have been the right way, you can avoid making that mistake by sticking with cross multiplying. All right, so that's it for separate and integrate. Yeah, we're done with that for today. And you can work on this assignment for a while. And then later in the block period, then you'll come back and revisit the next part of the notes.